So let me show you some tricky bits about this. Beware. The client that's initiating this connection might be malicious, and so might try to sneak through the firewall. So if you're not careful, if you just write a firewall policy that says, I'm going to look at the payload of each packet to this FTP server, and if it contains the word root, I'll block that packet, that's not sufficient. Because the client can arrange how they're going to split their data among multiple TCP packets. And they might split it up so that the word root spans a packet boundary. So the first packet has user RO, and then the next packet continues from there with OT, and then a password, and then a command. And neither one of those contains the word root. But when it's reassembled by the destination server, the FTP server, this turns into a successful login to username root. Here's another really tricky bit about doing this kind of enforcement on the payload data. Packets can be reordered. This might happen by accident, or it might happen because the client is malicious and is sending them maliciously in a particular order. Remember, the TCP uses sequence numbers to reassemble packets and reorder them. And so if they arrive out of order, no problem, the destination, the FTP server, will reorder them back in using the sequence numbers. So you could imagine that the attacker does the same as what was in the previous slide, but now sends the packets in the opposite order. So sends the second packet first, and then sends the first packet. If you're not careful, from the stateful packet filter, it will look at the first packet and see an OT. And if it's trying to reassemble the packets and reassemble them in the order they arrived, it will never see that the word root is there. So a stateful packet filter is going to need to keep track of the data sent along the payload and reassemble it and check whether there's the word root in that sequence, even maybe spanning multiple packets. And also we'll have to keep track of sequence numbers to reassemble them in the correct order so it doesn't get fooled by that. Okay, here's yet one more attack if you're not careful with building stateful packet filters and you're trying to do a policy based on the content. It can really get you into trouble. Let's imagine that we have a client, a sender, who's initiating the connection, who's malicious, and connecting to the FTP server. And the sender has created a TCP connection for FTP and has established it and has sent the user command and is now about to send the username. Okay. Now let's imagine that the attacker sends the next bytes of data with 1 byte per packet. So split up into a whole bunch of packets. So the next letter the attacker wants to send is R, the starting point of root. The attacker sends that packet. Now notice that IP packets, one thing to know about them, which I didn't really talk much about, is they have a field in there called the time to live, TTL. That's a hop count. It usually gets initialized to 255. And every time it goes through a router, that gets decremented. And if it reaches 0, the packet gets dropped. So that's a defense in there against packets traversing endlessly in some loop if there's a routing loop. We don't want the packet to continue circulating forever. So every time the packet gets forwarded by a router, it gets decremented, and this ensures that if it's initially set to 255, the packet will traverse at most 255 routers before it gets dropped, so it won't circulate endlessly. That's the intention, the design purpose behind the TTL, but the attacker is going to repurpose this and use it for malice. So the attacker is going to send this first packet with a TTL of 22. Why 22? Let's say the receiver is 22 hops away. It has to go through 22 routers. So that's just large enough that this packet will make it through to the receiver. Okay. Let's imagine the firewall is only 15 hops away. Okay. So this packet will make it through to the firewall and through to the receiver. So both the recipient sees that packet and the firewall sees that packet. So they both, in their reassembly of this TCP connection, they've seen the 1 byte R. They're in sync. Everything's cool so far. Now the attacker sends their next packet. The next letter they want to send is R, but the attacker is actually going to send a packet containing the letter N. But this time they're going to set the TTL to something smaller, 16. And that's just large enough that this packet will make it past the firewall, but then somewhere in the inside network, it'll get dropped because the TTL will go down to 0 after it's been seen by the firewall, but before it's seen by the eventual recipient. So the firewall is going to see this packet. The recipient won't. So the firewall thinks that what has been sent is RN. Sorry. This second packet will have the same sequence number as the R. So the firewall thinks that now there's been 2 packets sent with the same sequence number. So now the firewall has a decision to make. There's some ambiguity here. It sees there's an R and it sees there's an N. And imagine that this firewall is not looking at the TTL because it's not aware of this attack. One tempting strategy would be to say the firewalls should remember that what has been seen so far, the first byte is R. And if we see OOT, then that's bad. And that'd be reasonable if we assumed that the end host is going to discard duplicates, like keep the first packet seen in the case of a duplicate and discard the later ones. And some hosts behave that way. So that'd be a reasonable policy for the firewall to follow. But other hosts behave differently. There are also hosts that, in the case of duplicates, keep the last one. So if the attacker kept the first one, if the firewall kept the first one, but the end host is keeping the last one, now they're out of sync, and attack might be able to get through. Conversely, if the firewall keeps track of the last one that's seen, that'll work if the end host is also keeping the last one in the case of a duplicate, but it'll be insecure if the recipient uses the first in the case of a duplicate. So the firewall has an ambiguity and has to decide in their state, am I going to treat this as I've seen an R, or am I going to treat this as I've seen an N? So that's a pain. Now imagine that the next packet that's sent is an I. And this also has a short TTL, so it's seen by the firewall but not by the recipient. Well, then it looks like the firewall, depending on which of those 2 options you chose, either the firewall will think we've seen RI or the firewall will think we've seen NI. Now at this point, you might be really tempted to say, okay, it's hard to know how the end host is going to interpret this. Are they going to use the first or the last? So the firewall should actually clone its state. And remember, it could be either RI or NI, and I'm not sure which yet. I don't know which. If either one of those turns out to be bad, turns out to be the word root, then we'll block the connection. So that's a natural defense you might take against this kind of ambiguity attack. But check out what's going to happen next. Now suppose the attacker sends another packet. This time it's an O, this time with a larger TTL. Well, this one is going to be seen by the firewall and also will be seen by the recipient. So now there's 4 possibilities from the firewall's perspective about what the final reconstruction might be. It might start with RI, might start with RO, might start with NI, might start with NO. And maybe you can see where I'm going. I'm going to offer 2 options for every byte. And the number of possibilities that the firewall has to keep track of is exponential. So the amount of state the firewall has to keep track of, if you keep track of all possibilities, is exponentially growing. And that's a recipe for disaster. Okay, so this is a really tricky case because it seems like you're screwed no matter what you do. If you always choose the first you see, then you're going to be insecure for hosts that are choosing the last. If you always choose the last, you're going to be insecure for hosts that are choosing the first. And if you keep both, then your state, the attacker can drive your state to explode exponentially so that you're really hosed. Okay, so this is really tricky, and it illustrates a fundamental challenge with stateful packet filters that are based on passively monitoring packets, which is they have to predict how the end host is going to interpret this packet. And they got to predict it right. And if their prediction is wrong, or they get out of sync, or they have slightly different logic, then they might think that this should be allowed. They might think that the end result will be one set of data, but the end host actually ends up with something different than what the firewall was expecting. And so something might make it through that shouldn't have made it through. Okay, so this is pretty tricky to take care of. How does the attacker know how many hops there are? The attacker might not know, so they might try this attack once with guessing that the firewall is 15 hops away. And if that doesn't work, they'll try it guessing the firewall is 16 hops away. And there aren't that many possibilities, so the attacker can just try all of them. And if they succeed once, they're in.